Okay, so someone asked when and how do you recommend studying for the final? So, um, in all honesty, it depends on like how you want to go about doing it, when to start studying. People are different, so I'm not going to tell you like exactly when you should start. In my opinion, though, you should give it at least 2 weeks prior so that you can go back and relearn everything from the previous chapters that you probably dumped out of your brain into the ocean, like I did. Um, so give yourself enough time to go back and relearn like NMR, relearn chapter 12 and 11, which were kind of like the weird chapters. Um, and then the more recent chapters should be better in your memory, but also like don't start so far ahead that you don't learn this stuff that we're doing now, because then you have to kind of make up for that at the end. And then that wouldn't be good, but also don't wait until like 2 days beforehand, because if you try to cram like everything from the whole semester in 2 days, you're probably going to have a breakdown. And then I'll show you how I recommend studying in a second after we go through the agenda. So we're going to put a pin in that. Someone said, what were chapters 11 and 12? I got you. I'll go over that in a second. And then someone asked about how many questions it is. So I did not answer that yet. I'm not 100% sure because online it's a little bit weird. I believe the final, you have 2.5 hours. I don't know if you will get a 2.5 hour slot, but you should, because that's like the final exam time. And I believe it's 50 questions. Again, this could be slightly different because of the online format, but as far as I know, you guys will have the 2.5 hour-ish time slot, and it will be 50 questions. Okay, someone said they just looked and it's from 10:30 to 12:30. So, perfect. So 2 hours, not 2.5. That's my bad. Oh, yes, and that's a good point. So I know I do have people from the Tuesday, Thursday, and the Monday, Wednesday, Friday class. So make sure you are looking at your exam day and your exam time. So if I say something, I might forget that there's 2 class periods. So just make sure you're checking all of that. All right, so I'm going to go through the agenda real quick. You guys have had a lot of time to read it, so that's fine. I just want to let you guys know that we are going to focus on lactones and lactams today, and if we have time, we'll go through some example problems that are in the handout. So let's move on to this bad boy. Someone also said the syllabus says that there's 120 minutes with 65 questions. He might have changed the syllabus from when I read it, because when I read it in the beginning of the semester, I didn't see that. But I will look into that and let you know. I'm just reading questions, so don't mind me just staring. So someone said, are we reviewing stuff from last week? And then someone asked a question about last week. So yes, after we do lactones and lactams, we're going to go back and look at the reaction mechanism one more time. We're going to go over like the important points of it. And then I'm going to show you guys, because last week we did all the different steps of the reaction mechanism. It was kind of long and scary. So today we're going to spend the last like 5 minutes, and I'm just going to summarize it and show you the Rosemary method of how to do it really quick instead of going through the whole mechanism. So before we do that, I'm just going to go to an empty page, and I'm going to tell you guys how to study for the final. So this is a tip someone gave me when I took the class, and I found it to be super helpful. So this is like the chunking method. So you're going to chunk the material from the class into like 3 sections. So chunk 1 is going to be all the recent stuff that we are doing now. That's probably going to be I guess the most prevalent, like we talked about. So that's going to be chapters 16, 17, and 18. Sorry, I keep zooming in and out. I don't know what I'm doing. Chunk 2 is going to be all the stuff we did like in the middle that all kind of went together. So chapter 13, 14. I just decided to completely change what I was doing. So chapters 13, 14, and 15. And then chunk 3 is going to be, what's happening? Chapters 9 and 11. So chapter 12 was technically in this, wow, why did I put 19? That's my bad. Chapter 12 was technically in this like time chunk of the class, but I'm actually going to put it here. And that's just because the material from chapter 12 more so fits with this stuff than it does here. So the way I recommend doing it is right now we're learning this stuff anyway. So stay on track with this stuff, study this chunk first, and go back to chapter 12, look at the concepts and the reactions, and then tie that into what we're learning now and kind of make connections about what's similar and what's different. And then after that, I recommend doing chunk 2, looking at conjugation, aromaticity, electrophilic aromatic substitutions, all that kind of stuff, because all that kind of went together. And that's like, I don't want to say the second most important, but in terms of studying time, I would place that as second most important, just because there is a lot of material. And then the last thing I would go through is chapters 9 and 11. Chapter 9 is obviously NMR, and chapter 11 was like alcohols, ethers, and then reactions of alcohols. So like dehydrations and making alcohols, things like that. And so the reason I put these last is because everything else goes together. So like all these chapters flow together, but chapters 9 and 11 are kind of like on their own. They're kind of gross. Like they make sense, but it's just like random stuff. So that's why I would study those last after you've gotten all these concepts down and you kind of built this nice foundation. That was a lot. Do you guys have any questions? Obviously, this is just my opinion. This is what I felt helps a lot of students. So this is not how you have to go through it. I just find that to be helpful. I'm also going to send you guys the attendance link. And then someone asked, is the final really hard? I wouldn't say it's like super hard. It's not like Orgo 1 and 2, so that's great. You don't have to go back and learn Orgo 1 stuff. It is a lot because it's cumulative and there's a lot of stuff you have to review, but in my opinion, it's not as bad as people make it out to be if you study and you kind of connect ideas the way I tell you guys to do. And then someone said, when will we be done learning new material? Hopefully soon-ish. Just so that we have more time to review together, but I am not sure. We should be done with chapter 17 this week, and I'm hoping we can do chapter 17 or chapter 18 next week, and then we have 1 week to review, but that's just my tentative schedule. I'm not sure. Someone asked about, in my opinion, what's a good timeline for covering all the material, like when you should have chunk 1 done, etc. So I would say like you guys should be studying kind of as you go, but I know that's kind of an unrealistic thing sometimes for people in college. So if you start like 2 weeks before the final studying for real, I say spend like half of the first week going hard on chunk 1. Yeah. And then the rest of the first week going into chapter 13, and then spend a couple more days on chunk 2 in the next week, and then spend the last half of the next week on chapters 9 and 11, if that makes any sense at all. Okay, so someone said it's exactly 4 weeks before the final, so we should study right after Thanksgiving then. Pretty much. Honestly, I would, again, this is just my opinion. You guys don't have to do this. I'm not telling you what to do. But in my opinion, I would probably take that Thanksgiving time off, and use that to get ahead on the studying. But I know you guys are taking a million classes and you guys have family and stuff. So yeah, if you're busy that Thanksgiving time, right after Thanksgiving, I would start studying. All right, there are a couple more really good questions, but I do want to get through this material first that we wanted to cover today. And then if we have some time at the end, we can answer a couple more questions. Sound good? And I assume, I forgot to ask, but I assume you guys can all see my screen because you were asking about that stuff. So yes, okay, cool. So let's scroll back up. I really hope, like, I am always really afraid that when I scroll like this, it's giving someone motion sickness. So I'm really sorry if that happens. And someone said, did I just cover the reaction mechanisms on Friday? So yeah, pretty much essentially, we just went over this. And if you weren't here, I'll give you a second if you want to screenshot it or anything. But we pretty much just did naming and the main reaction mechanism for chapter 17. Alrighty. So lactones and lactams, these are my favorite because they're super easy. So essentially, we're just going to first look at what is a lactone versus what is a lactam. Sorry, I choked on my water. All right. So you guys should know what a lactam is, or at least kind of have that seed implanted in your brain, because we talked about it in chapter 12. So you guys think group 1 is lactones or group 2 is lactones? What do you think? Or first, if you guys want to tell me, what were lactones? Like, what was the functional group? Cyclic esters, exactly. So let's write here. Lactones. Cyclic esters. And I guess I kind of ruined it because I wrote it next to the group. That's okay. So if lactones are cyclic esters, and we know that that's this group, what do you think lactams are? What's the functional group for a lactam? Cyclic amide, awesome. Alrighty, so we know cyclic esters are lactones, cyclic amides are lactams. And so when we go about naming them, the best part is all of these are just going to differ by one letter. And what I mean by that is, I'm going to zoom in. So what do we call the carbon that's directly next to the carbonyl? What's our special designation for that? Alpha. Awesome. So then after alpha, we have beta. And then we have, does anyone know what comes after beta? Gamma. Wow, nice. So yes, gamma. And then after that, we have delta. So remember that order. The way you name a lactone or a lactam is you just go up to the highest letter and you put that in front of the name. So delta, lactone. And underneath, I'll write it this way, just in case. Ta-da! What do you guys think of that? Are we happy with that naming? I hope so. Yes? Okay, cool. So for this next one, we have alpha, beta, gamma. So what do we think this lactone is going to be called? The gamma lactone. Awesome. Perfect. So as we go one size smaller, we have our lovely square. So we have alpha, beta. So what do you think this one's going to be called? The beta lactone. Perfect. Alrighty, last but not least, what do you guys think this will be called? Awesome! Yes, it is the alpha lactone. And just like that, you guys have learned lactones. Congratulations. Pat yourself on the back. Did amazing. Now we're going to take the same exact idea. I'm just going to move this a teeny tiny bit. So we're going to use the same exact idea to name lactams. So what do you guys think this lactam will be called? The delta lactam. Awesome, because we have alpha, beta, whatever, gamma, delta. This is our delta lactam. Next up, one size smaller, what do we think? Gamma lactam, yes. Alrighty, what do you guys think of our little square? Beta. Perfect. All right, last but certainly not least, what do we think of that guy? The alpha lactam. Sweet. Perfect. Couldn't have said it better myself. Oh, I got too excited. I knocked over my camera. Or my laptop. Alrighty, so that's pretty much it. That's how you name lactones and lactams. I just want to reiterate and stress one more time. Lactone is the cyclic ester. Lactam is the cyclic amide. Amide. That's how I like to think about it. Someone said super easy. Wow. That's what I go for. Try to make your lives as easy as possible. But Dr. West, on the other hand, he needs to make sure you guys know what you're doing. So he's going to ask you this in a little bit more of a difficult way. The only way to really make this difficult is to put it in condensed form. Ew. So we're going to go over how to do this in condensed form in like 2 seconds. I just first want to answer a question. So someone said, would they ever add substituents to these? So they could add substituents when you're making and breaking lactones, but as far as naming goes, no. This is all you're going to have to name. Okay, so I'm going to make an extra page, and we are going to very quickly go over making and breaking lactones. Same exact rules go for lactams. I'm just going to draw it out once, just because I don't want to draw it out twice. Does anyone remember what kind of reaction we were doing in chapter 12 when we broke lactones? Ooh, yes, someone said intra, and I think you mean Williamson ether. Yes, a couple of you guys said that. Awesome. So that is how we make lactones. Why did I do that? So when we make lactones, one of the ways we can do it, well, not necessarily the Williamson ether synthesis, but something kind of similar. All right. Well, yeah, it's kind of like the Williamson ether. Okay. All right, so let's say we have a long chain like this, right? In the Williamson ether synthesis, what did we start out with? And someone asked, it's the same for lactams? Yes, it is. So someone said base, yes, but for the intramolecular Williamson ether synthesis, what kind of molecule did we have to start out with in order to make the ether? Yes, the alkyl halide. So we're going to have something similar, except we're going to do something like that. So now instead of just having a halide, we have the acid halide, and we're going to have an oxygen somewhere else on the ring, like so. So we're going to take this reaction, and it's going to be very, very similar to the Williamson ether, except we're going to put the concepts that we learned in the nucleophilic acyl substitution reaction. So this is an acyl halide, or an acid halide, excuse me. And so how reactive are these carbonyls? Super reactive, meh, or not reactive? What do you guys think? Very, very super reactive, exactly. So we are going to do a nucleophilic substitution, but it's going to be intramolecular. And so all that means is we attack here, and we are going to kick up these electrons. And the most important thing at this point is counting your carbons. So we have oxygen. We know oxygen is going to be in the ring, so I'm going to actually start there. So 1, 2, 3, 4, 5. We stop at that carbon because that's where we attacked. So we know we need to make a 5-membered ring with an oxygen inside of it. So I'm going to zoom out a little bit. Just for like cleanness sake and having everything the same, I always put the oxygen here just so I can orient myself. So in reference to the oxygen, we know our ketone was here, right? But remember, we brought those electrons up. So now we have a negative charge. And we also had chlorine here. We also have a methyl substituent on carbon 2. So let's go ahead and number everything again. So 1, 2, 3, 4, 5. So we know our methyl goes here. At this point, what do we want to do? What do you guys think? Remake the double bond. Awesome. So we're going to drop those electrons down and kick off the chlorine, like someone else said. Awesome, you guys. Or gals, or people. Okay. So once we reformed the double bond, we can go ahead and draw the rest of the ring exactly the same. Ta-da! And ta-da. So now we have our lactone. We also have Cl- floating around. but we don't really care about that. So this is how we make a lactone. Any questions, comments, concerns, anything like that? Oh, that's a good point. Someone asked, where did the H on the OH go? So that would be here. You're totally right. That would still be there. I just got rid of it because I'm used to just doing that. At this point, we would have our Cl minus, and that would come in and steal the hydrogen. I don't know why it was so hard to say hydrogen just then. And now we have our happy group. Thanks for pointing that out. And somebody name this lactone for me, please. Remember what I said about substituents? Awesome, yes. So this will still be a gamma lactone. Awesome. Perfect. So it seems like you guys got this. So let's do breaking. Oh my God, why can't I write? So when we are breaking lactones, we're essentially going to do the opposite reaction. So let's start with, why not? That's fun. What is this called, please? What kind of lactone is this? Beta, awesome. So it's our beta lactone. And if you guys remember, way back in chapter 12, we did reduction reactions, and we did reductions with esters, and we actually did an example where the reduction broke open a lactone. So we're going to do a very similar thing now. Does anyone remember a reducing agent that will work for esters? Ooh. And if you guys will notice, at this point, I'm going to start bringing back other concepts from past chapters so you guys can start making connections. So that's why I'm asking all these questions. So LiAlH4, perfect. So that is our reducing agent. What is our reducing species? H minus, yay. Awesome. So yes, H minus will be the nucleophile. So it's going to come in and attack this carbon. We kick up the electrons, excuse me. And we get O minus. I also forgot to write it, but we do have H2O in solution, just in case anyone was wondering. So now that we have added this hydrogen, what is our next step going to be? We can either protonate or we can drop the electrons down. What do we think is a better option? Okay, someone said protonate. That's valid. But someone else said drop the electrons. So why do you think dropping the electrons might be better than just protonating? Because sp2 is more stable. Awesome. Perfect answer. So while we definitely can protonate this, the best thing that we can do is actually bring these electrons back down, and we end up breaking open the ring. So at this point, again, we're going to count the members of our ring. But since we're breaking it open, I'm not going to count the oxygen this time. It just makes more sense to me if I just count the carbons. So now we have 3 carbons in our chain. Ta-da. And I'm going to say this is carbon 1, 2, 3. So on carbon 1, what do I have to draw in? You guys, please tell me. The carbonyl, 100%, exactly. And what is attached to that carbonyl carbon? The hydrogen we just added. Awesome. Perfect. And what is attached to carbon 3? O minus. Perfect answer. Awesome. So at this point, what can we do? Protonate, yes, for sure. So we have H2O in solution. Or we can have an acid. Oh. Or we could have an acid, but in this case, H2O is fine. So the negative charge steals the hydrogen, gives those electrons back to oxygen. So now we get, I'm actually going to change this arrow and write it downward because I didn't give myself enough space. So we get the same chain, protonate, and we have our carbonyl. Okay, so someone asked a really great question, so I'm just going to zoom out. They asked, why couldn't we just do intramolecular proton transfer in this case? So the reason we can't do that is because in order for us to be able to do an intramolecular proton transfer, you need an extra proton somewhere. So yes, in this case, we have a bunch of protons like on the molecule, but we don't have any extra. So we're never going to remove a carbon-hydrogen bond. We're never going to break this aldehyde bond. So in this case, we have to go and use the catalyst. Make sense, sort of, kind of? Okay, perfect. So at this point, are we done? What do we think? Okay, so you guys said yes, which would make sense, except please go back to chapter 12, brains, right? So what's the rule if we use a strong reducing agent? What's our final product going to be? Strong reducing agent plus an ester. It repeats the reaction and you get a primary alcohol. Awesome. So we're going to have to do this one more time. And we already know what this reaction looks like. So I'm just going to say one more time. And we are going to get our OH on the end. That one doesn't change because that was the oxygen that was inside the lactone. We've added 2 hydrogens. And now we have a primary OH. Ta-da! Now we have reached our final product. Any questions whatsoever? We could have also broken this in a chapter 16 reaction or a chapter 17 reaction. which we'll see later on, both of those kind of things. I just wanted you to review chapter 12 concepts because this is a very common way to break a lactone. I will zoom out so you guys can see making and breaking on the same page. We're going to go up and do that one exam-like practice problem, and then we will end the session by reviewing the reaction mechanism. Cool? Any questions, comments? Alrighty. Where'd it go? There it is. So this question is asking us which one will form a gamma lactone, and you guys can see it, so I'm not going to ask. But the gamma lactone is a 5-membered ring. So I like to always remind myself that, just so I don't make any mistakes. And there's actually 2 ways that we can do a question like this. We can either draw them all out, or we can do it the condensed way. And I'm going to show you 2 of the answer choices in the long way, but I'm also going to show you the condensed way. So when you guys practice the first couple times questions like these, I want you to draw them all out. And then after a while, you should be able to just do it in the condensed way, because that's a lot faster. So let me draw out answer choice A. We have an alcohol with 1, 2, 3, 4 carbons attached to it. And attached to that last carbon, we have an ester. So if we were to do the reaction and make the lactone, we know that this would attack here, and we would end up with a 1, 2, 3, 4, 5-membered ring. So for now, that one makes sense. Any questions on how I got that? I know I did it super short compared to the reaction mechanism we just did. Everyone's good? Yes, I can definitely repeat that. So essentially what I did is I drew out this thing like so. And looking back at our reaction mechanism that we just did, I know essentially the oxygen will attack here at the carbonyl carbon, and we end up making a ring, right? So instead of drawing the whole thing out, I was able to count how many spaces there are between the carbonyl and the oxygen, which is 1, 2, 3, 4, 5. So I knew this would end up making a 5-membered ring. So I know this will be my answer. And then someone said if we were to go through the mechanism, the ester would get kicked off. Absolutely. So the ester would get, well, I don't want to say the whole ester will get kicked off because then that might confuse some people. But this part of the ester will absolutely get kicked off, and you end up with this byproduct. But we don't ever really draw it out because we don't really care about it. But yes, you are absolutely 100% correct. Awesome. All right, so answer choice B, if we do it the long way, we have 1, 2, 3, 4, 5, 6 carbons off of carbon 2. We have an OH, and at the end, we have an acid halide. So if we follow the same idea, I'm going to zoom in, where the nucleophile will attack, wow, that was a weird arrow, will attack the carbonyl carbon. We are going to make a 1, 2, 3, 4, 5, 6-membered ring, which then gives us this guy. So we said that this one was okay because we were looking for a 5-membered ring. What kind of lactone is this? delta. So we know that this cannot be the correct answer. There is a methyl. I just didn't draw it because we don't really care about it, but yes, it would be right there. You're correct. So for C and D, I'm going to show it to you in the short version. If anyone needs me to repeat it or anything, let me know. So instead of drawing out the whole thing, I can see that one, we have our carbonyl carbon right here. This is a whole lot of other stuff going on. We don't care about it because we know that this would be a carbonyl, and then this is just some stuff attached to it, right? So we know our oxygen is going to attack here, and we will make a 1, 2, 3, 4-membered ring. So what kind of lactone is that? If there are 4 members in the ring. And 4 members is including the oxygen. Beta, exactly. So this would make a beta lactone. We know that that's not correct. I'm going to zoom in again. Last but not least, we see that this is our carbonyl carbon. Obviously, this is our oxygen. Attack. And we get 1, 2, 3 members in our ring. A 3-membered ring will be what kind of lactone? Alpha, exactly. So this also cannot be correct. So our correct answer has to be A. And we just went through and learned 2 different methods of getting the answer in a question like this. Any questions? Anything you'd like me to repeat? I'm also going to send the attendance link one more time, just so you guys can fill it out whenever you get the chance. All right, so if we don't have any questions on this, someone said he always attacks but never protects. That's funny. Alrighty, so we're going to do a 1-minute summary of this stuff. So the long reaction with all the intermediates and stuff shows us that in an acid catalyzed reaction, the electrophile becomes more electrophilic. And then it has a positive charge, and then the nucleophile is able to attack. At this step, we get a intramolecular proton transfer. And then when we were here, we saw that there were a couple different things we could have done. So we could have either dropped down the electrons of, wow, my iPad freaked out, of the oxygen, which would give us an amide, or we could drop down the electrons of the nitrogen, which would give us this weird imine kind of thing. And so we know that amides are super stable, and we've never seen this thing before. So we went with the amide. And we got our final product. So the fast way to do this, so I want you guys to do the mechanism when you're studying, but I want you guys to get to a point where you can look at this and you can say, hey, leaving group, nucleophile, ta-da. All you're doing is taking the nucleophile, cutting off the leaving group, and pasting the nucleophile. So that is pretty much the basic summary of nucleophilic acyl substitutions. So I will stay on here for a couple more minutes for questions if you guys have any. But that is pretty much all the content I wanted to cover today. And also, I realized that was Jared who said the attacks thing, and I'm so sorry, Jared. I didn't recognize your name for a moment. Jared's awesome. Props to him. You're very welcome, guys. Have a great day. Enjoy your Monday. take a nap. So yes, someone asked, are you going to be reviewing for the final? So we have something called Up Owl Night, which I'm going to send you guys an email about. It's essentially a thing the class office holds where everyone gets a 2-hour review session and 1 hour of tutoring for the final exam. The schedule, I'm not sure if they sent it to us yet or if they made it public to you guys yet. I believe we received it, but you didn't. So that information will be going out to you guys soon. I think Katrina and I decided that we're going to split the material. So she's going to have half of the material and I'm going to have the other half, just so we have more time to cover everything, because like 9 chapters is a lot in 2 hours, or however many chapters it is. But again, we will send all that information to you as soon as we can. We just have to sort out a couple more things. And then someone asked, for the last question we did, couldn't we have just counted the carbons in the answer choices? So yeah, that's pretty much what we did for C and D. We just counted how many carbons there are between the oxygen and the carbonyl carbon. So yeah, you can do it that way. And then someone asked, so all we need to know for the nucleophilic substitution is the product. Pretty much, like conceptually, you should know why things happen, because he could ask you something like, I don't know. I'll try to think of a concept question. He could ask you something conceptual, so just understand the idea behind it, but you only really need to know the product. You don't need to know the entire mechanism. You're very welcome. Goodbye. I don't know where the accent came from. Okay, so I'm going to stop recording now.